response functions of a system, the linear response functions both in continuous time and in discrete time. And some of those response functions we have looked at unit impulse response function. We have, or rather impulse response function, step response function, and pulse response function. And we have we looked at the same. We looked at the same in continuous time and in discrete time, and we were able to develop or to see how a discrete convolution equation can be created from the three response functions. And we saw also some characteristics of these response functions, which are a solution to which are usually a solution to the storage outflow, the storage discharge function of linear systems. And we said the principle of proportionality, the principle of, which was the other one? Superposition, such kind that. And, you know, whereby if a solution is X, then 2 of X, for example, or you can say then Y of X is also a solution. Any, you know, multiplied by any constant is a solution. And we also saw another solution could be X plus 2 of X, for example, you know, the principle of superposition. And so initially we did the instantaneous unit hydrograph. We looked at the use of the application of the convolution, discrete convolution equation to derive a unit hydrograph. And in one of the examples, we have a convolution. Actually, the convolution equation is used to calculate this discharge Q, and the deconvolution equation is the one that is used to calculate the unit hydrograph. Then we looked at synthetic hydrographs, and why? Because I said in order to apply the convolution equation, you will need a measurement of discharge, both discharge and rainfall. But in some cases, and that is a very common situation in our country, you find that we do not have data, discharge data that is measured. So this is where the synthetic unit hydrographs come into play. That is where they are used. And that is why they have been developed so that they can be used in cases where we do not have discharge. So how are they developed? The previous one, the Snyder's synthetic hydrograph, studies were done in so many gauged catchments. And when we talk about a gauged catchment, we are talking about a catchment where data has been collected. And relationships, various relationships of unit hydrograph and various geomorphological characteristic of the catchment or the drainage area were determined. And, you know, from that, that is where now we came and saw relationships like time lag, basin lag, time basin lag, things like the width of the hydrograph at 75% level of the peak discharge, and at 50% discharge, you know, the hydrograph have at 50% of the peak discharge. And the base time of the hydrograph. And I'm seeing my connection is weak. So if I start breaking, you can tell me so that we do not lose a lot. So that was the Snyder's. So it is all about a matter of correlating the standard features of the standard unit hydrograph, features of the standard unit hydrograph, and features of the required unit hydrograph. Then the second hydrograph then is the SES hydrograph. SES means Soil Conservation Service, and it is for the US. It is for the United States. And the same with Snyder's hydrograph, also that empirical approach, the study was also done in the United States. But the Snyder's unit hydrograph has received widespread application all over the world, in most parts of the world, and especially in Africa, where we have many engaged catchments. So I want us to talk about this SES method, dimensionless unit hydrograph, and then we are going to discuss about our schedule, and we make a final determination because I have to, I'm seeing now. Yes, I should have been breaking, but now I can see the connection is a little bit stable. So, so the SES dimensionless hydrograph is a synthetic unit hydrograph in which the discharge is expressed by the ratio of discharge Q to peak discharge QP, and the time by the ratio of time T to the time of rise of the unit hydrograph TP. And the following diagram should be able to help us explain this concept a little bit clearer. Yes, so if you are given the peak discharge and the lag time for the duration of the excess rainfall, then you can be able to determine the dimensionless hydrograph or given basin. For example, In this figure, we have a dimensionless unit hydrograph. That is the part A of this build. Hey, what's happening? Haitoki. Okay. Okay. Yes. So on the left-hand side, we have a dimensionless unit hydrograph, which has been developed from unit hydrographs from many similar watersheds. And in this kind of dimensionless unit hydrograph, you notice one thing. We have the Q out of QP ratio. And then we also have the relationship of the time lag. We have the relationship of the time lag. And in addition to this, we can now correlate the peak discharge and the basin time lag. So you can correlate discharge and ultimately now correlate the peak discharge with the time to peak, and that is usually called the basin time lag. Now, usually, according to the SES method of estimating, or the SES unit hydrograph, or rather what we call the SES dimensionless unit hydrograph, the values of QP and the value of TP can usually be estimated using a simplified model of a triangular unit hydrograph, which is shown in the second part of the image, where the time is in hours, yes, and the discharge in the y-axis is in meters cubed per second. According to the SES method, they have suggested that of recession, that is the falling limb, this particular part of the hydrograph. This is the recession part. We have a rising limb and a falling limb. So they estimate, of course, we have already seen the correlation between QP with TP, but what about the other part of the hydrograph? Because the total base time of the hydrograph is TP plus the falling limb, and they have estimated that this part can be estimated by 1.6 multiplied by TP. Now, for all the hydrographs, whether the SES method hydrograph, whether the Snyder's, whether the other one, the area under the curve should always be equal to 1 unit, or rather 1 centimeter. But basically 1 unit. You have to know which unit you are using to calculate this hydrograph. And they have been able now to show, given that kind of background, they have been able to show that the peak discharge is given by CA divided by TP. TP is the lag time of the basin lag time, or essentially time to peak, since the start of the rainfall, since the start of the rainfall, since the centroid off, since the centroid of the rainfall. Notice here the time here is TR over 2. So that means since the rainfall started and the rainfall duration is TR, or what it is yes, it is TR. So since the centroid of the rainfall duration, that is the time lag. And C is given by 2.08, but I told you people that I have to confirm these units because they are dependent on whether they are the European imperial units or English units. And I'm thinking here I'm using the imperial units as opposed to English units. And A is the drainage area. In addition, the basin lag time, TP, has been estimated as, and it is the time from the end of the rainfall to peak, from the end of the rainfall to the peak. So this TR, this bar shows excess rainfall. This bar shows excess rainfall. And sorry, the hydrograph starts from time 0, from the start of the rainfall. So the basin time lag TP is approximated as 0.6 TC, and TC is time of concentration of the watershed. And what is time of concentration? From engineering hydrology 1, we just did it the other day. Anyone who can remind me what is time of concentration? Anyone? Time of concentration is the time it takes water to flow from the farthest point of the catchment, to the outlet of the particular catchment. So the time it takes water to flow from the farthest point. Now, why is this one very important? Because if you have a rainfall with a duration equal to the time of concentration, you are going to most likely record the largest peak during that time, because all the catchment will be contributing to runoff. So let us try to apply these 3 concepts. It's very easy, this one. It's very easy. And normally when you are dealing with these synthetic hydrographs, some of the critical questions, in addition to applying it, because essentially, if you get a problem, you will be required to develop this kind of a hydrograph. So essentially, you are going to just develop a triangular hydrograph. Some of the other questions that can arise is calculation of, say, QP. Separately, calculation of the TP, you may be required to calculate TR and so forth and so on. And normally you find that you may be given the time of concentration, for example. So if you're given the time of concentration, you can easily then, and you know the duration of your rainfall, you can easily calculate TP. And if you have TP and you have your constant, you have your basin area, you can easily calculate your QP. And that is all that we need, because that then for the hydrograph, in the y-axis, you will need to determine QP. You will need to determine TP using this formula, and then you will be required to determine 1.6. You will need to determine that point. Let me just, try to draw with a different color. So you will be required to determine this point, that is the QP. You will be required to determine TP, the point. You will be required to determine 1.67 after TP, that is that point. and you can, with that, you draw your hydrograph. Now, after you have drawn it, you can now make it into a sample data if you want, or a discrete data that you can use. When I'm talking about discrete data, I'm talking about discharge, for example, every hour. Meters cubed per second, meters cubed per hour, and such kind of things. Because now you see here we have a continuous line, but when now we are extracting this kind of data, we want to know meters cubed in the first hour, in the second hour, and such kind of things in each hour. So we have an example. And we are required to construct a 10-minute SES unit hydrograph for a basin of area this and time of concentration 1.25. So what do we need? We need to determine QP, we need to determine TP, and we need to determine 1.66666 TP. So we apply those three equations. First, we started by calculating TP. Then from TP, we calculate capital TP, and then from capital TP to QP. And then finally, we calculate 1.67 TP. So those are the variables only that we need to determine. I don't know whether I've given the dimensionless unit hydrograph anywhere. Yeah. So you can plot this. And this is an exercise I'm going to give. We can plot this into a similar graph like this one. So this is an exercise I want us to go and do from the solution. From the solution that we have, let us draw the triangular unit hydrograph for this particular case. And one thing that is coming out is we can now convert the dimensionless unit hydrograph, or rather what we do now, how are you going to draw it? You are going to draw it by just converting this hydrograph into the required units. And what are the units and what are the quantities? The quantities are calculated here. So and finally, in order to finish your analysis, you need to do to check that the depth of direct runoff is equal to 1 centimeter. And how do you calculate the depth? It's the mass density curve, or the area under the curve, or rather a half base times height should give you 1 centimeter. Now, I want you to notice one thing. In these units, and you will notice I've talked about 1 centimeter all the time. In these units, for example, for the QP, it is 7.49 meters cubed per second per centimeter. If you are using rainfall in millimeters, it will be per millimeter. If you are using the rainfall in meters, it will be per meter. So that one should be very clear, because you can always make using different units. Then if you do that, then the area under the curve will be either 1 millimeter, 1 meter, 1 centimeter, based on your units. Okay. So we look at, let me see, slide 15. We can finish just these other slides. We can just finish these others and then we can go to our calculation. Now, how do we calculate unit hydrographs for different rainfall durations? So, for example, unit hydrograph is a unit hydrograph resulting from one unit of rainfall. So how do we do rainfall for different durations. We do this by applying the principles that I've just explained, the principles of superposition and proportionality. What do we mean by superposition? And a sum of two solutions are also a solution. What is proportionality? A multiplier of a solution is also a solution. Basically, that is what the principles mean. And we use this by generally applying the S hydrograph. Is the S hydrograph, and normally the S hydrograph is obtained by adding a number of unit hydrographs. Basically, what we have here, this is the S hydrograph, and we obtain it by adding so many unit hydrographs. Now, if you lag the S hydrograph by a time dt and you subtract, you are going to get a unit hydrograph of time dt. So you have developed an S hydrograph, but assuming you have measured the rainfall for a duration dt, and where dt is more than 1 unit, whereby dt is more than 1 unit, then if you subtract those two curves, you are going to get a unit hydrograph of duration dt. So remember, the response at time t to a unit pulse of duration 1 beginning at time 0, beginning at time 0, and it is usually given as h of t, and we calculated it as h of t is 1 over dt, gt minus gt minus dt, t minus dt. And if I can go back to where we did it so that it's a little bit, it is in the first one. Yeah, so I'm not going to open it. Go to the notes, stream hydrograph analysis part 1. That is where it is. But basically, h of t is 1 dt, g of t minus g dt. Peter Jeroge, you have a question. If you lag, and I've you know, I think I've explained that if you lag the same S hydrograph by time dt, that is h is equals to t minus dt, then the t becomes, the t in the h of t becomes t minus dt. So that now the t minus dt here becomes t minus 2 dt. And if you now thinking about a third unit pulse beginning at time 2 dt, that is t minus 2 dt, then here you are going to have 1 over dt, gt minus 2 dt into g minus, into t minus 3 dt. And you can continue this indefinitely by summing the resulting equations. And if you rearrange, you will end up with the solution g of t is equals to dt h of t plus ht dt minus dt plus h of t minus 2 dt plus h of t minus 3 dt, and so forth infinitely. Why do we have D of t on this part? Why we have G of t, D of t on this part? What we have done, we want to make the G of t, we want to make the G of t the subject. So we multiply D of t, dt, we multiply dt on both sides, and on the right hand side it cancels, and then d of t becomes a constant before each h of t function, before each of h function, because what we are interested in is the g of t. What we are interested in is g of t. So essentially, what I was just trying to say, and this is a repeat of what we did in the analysis one, is just this figure, and what we have just learned is to log gt with time dt, is to log gt with time dt. Now, notice in an ideal situation, the S hydrograph is supposed to be a smooth curve. It is supposed to be a smooth curve, but this may not always be the case, because we know, like I stated before, of course, when I was explaining about hydrologic flows, I said that they largely follow linear models, but I also gave a caveat, and I gave, some limitations, or, some, because that is the assumption, assuming a general situation, an ideal situation, a smooth surface. But because of the various hydrologic processes and interactions of water with the landscape, most of the time that is not the situation, and you may end up having some level of non-linearity relationship. Now, and in that case, you are going to not have you will not have a smooth curve, or you will have a S curve which is undulating, because of a number of things. If there are errors in rainfall abstractions or base flow separation, and those ones are expected, because how do we calculate base flow, for example, rainfall abstractions? The various methods that we did in engineering hydrology 1, we can use the runoff coefficient method, phi index method, and also we can use abstractions using infiltration equations. And all these are approximations. And because of that, we may have errors. We have also base flow separation, and we have a number of base flow separation methods. We have using the curve, the normal curve method. We also have using the graphical methods, the straight line method, the fixed base method, and there's another method I cannot remember. We have a number of 3 of them, and all of those methods are approximations. So anytime we have an approximation, that means we have errors. Another reason why we are going to have a not smooth curve is if the actual duration of excess rainfall is not the derived duration for the unit hydrograph. And is that possible? Yes, it is. And I will give an example. When we are measuring rainfall, for example, using these automatic measuring methods, like for example, if we're using the tipping bucket, we know the bucket only tips when the cup is full, has received, let's say, 2 millimeters of rainfall. If it does not receive 2 millimeters of rainfall, the cup does not fall, and it will not be counted. So that means using that method somehow will produce errors, and sometimes rainfall may end up being measured and especially that rainfall that was not measured, which is still stored in the cup because the cup was not full, is not going to be counted. So there's going to be that error of the duration of rainfall, or rather the rainfall that was measured is not equal to, is not, what should have measured for the particular duration of rainfall. There is, if there is non-uniform temporal and aerial distribution of rainfall, and what are we talking about? If we are doing a unit hydrograph, and I want to give a very extreme example of Tana River. Tana River starts from Mount Kenya, and Tana River discharges in the Lake Victoria. Tana River starts in the highlands, where we most of the time have rainfall, flows into the towards northeastern, and then flows southwards to the Lake Victoria, to Indian Ocean. Sometimes you'll have rainfall falling in the highlands, and we do not have rainfall in northeastern, for example. Sometimes you have rainfall close to the delta, in the Tana River Delta, and you do not have rainfall elsewhere. So when we are developing these unit hydrographs, we are assuming that the rainfall is falling on all parts of the catchment. Then when the natural data are not linear, and I think I've explained a little bit about that linear. I've explained a little bit about that linearity. Sometimes in ideal situation, we expect linear relationships, but that is always not the case. So once you have made the S hydrograph, you can then derive the unit hydrograph of a given duration using the two procedures mainly. One, you advance or offset the position of the Hess hydrograph by a period equal to the desired duration dt. Then, and you call this one an offset S hydrograph, or rather a G prime of T. And G prime of T will be defined by G of T minus dt. I think you just ignore this one. It's just a repeat of what I've written. Then in step 2, you subtract now G of T minus dt. You subtract G of T minus G prime of T. You subtract G of T minus G prime of T, and this will give the desired unit hydrograph H prime of T, shown in and calculated in form of equation 17. For example, we have one example, and actually this is usually not complicated. Most of the time what is complicated is the derivation of the unit hydrographs. The lagging of it is not an issue. So I don't know, you have been given a 5 hour, a half-hour unit hydrograph in this table 6, not 3, to produce. We are required to use this 0.5 hour unit hydrograph in this table to produce the S hydrograph, and a 1.5 hour unit hydrograph for this watershed. So how do we go about it? In order to determine the S hydrograph, G of T, that is column 3. So what is given in this particular case is the time T and the unit hydrograph, the 0.5 hour unit hydrograph. So to get the Hess hydrograph, G of t is given by dt times h of t. This is h of t. So G of t here is equals to 404 times 0.5, which is 202. For t is equals to 1 hour, G of t is equals to h of t plus h of t minus 0.5. And this will give you basically 0.5 times 4 plus 10 plus 4, sorry, 0.5 times brackets 4 plus 1079, and this gives you 742. For the case of 1.5, you are going to have G of t is 0.5 times 4 plus 1079 plus 2343, bracket, brackets, and so forth and so on and so on, and so forth and so on. Don't know whether that is clear. It should be etc. And then you fill this part. Then you log S hydrograph G of t by time dt. We want to create a 1.5 hour. So you log the whole of this. We are logging the whole of this by 1.5 hours. So essentially, you just move this data downwards 1.5 hours. And then finally, we calculate the 1.5 hour because it's going to be G of t minus G of t minus dt. And how is that done? For example, for t is equals to 2.0 hours. Remember now our d of t is 1.5. Our d of t is 1.5. And we are going to be subtracting, for example, 202 minus 0 divided by 1.5. And let me use my calculator. 202 divided by 1.5 should give you 134. Yes, so you're going to get 202 minus 0 divided by 1.5, that is 135. 742 minus 0 divided by 1.5, 1913 minus 0, that is 1275. 3166 minus 202 is equals to 1976, and so forth. And you do it until the end. And finally, you plot. Your 1.5 hour unit hydrograph. You can plot it or you can leave it. But now this is the 1.5 hour unit hydrograph. Any question about this one? Because now I want to talk briefly about an instantaneous unit hydrograph. It is going to be brief because we are going to have very little application for it in our course, in our subject, and then we can finish. Any question? So like I'm saying, I want us to finish with the instantaneous unit hydrograph. And if the excess rainfall is of unit amount 1 and its duration is infinitesimally very small, then the resulting hydrograph is an impulse response function that we call the instantaneous unit hydrograph. Essentially, then, what we are talking about is the excess rainfall is applied, in this case, to the drainage area in a zero time, approximately zero time duration. Of course, this is only theoretical. Probably none. It has not been encountered in real life, but it is useful because an instantaneous unit hydrograph characterizes the watershed's response to rainfall without reference to the rainfall duration. And then because of that, the instantaneous unit hydrograph can easily be related with the watershed geomorphology. Basically, the instantaneous unit hydrograph can be calculated using the convolution integral using the convolution integral, where this particular component of this convolution integral is the instantaneous unit hydrograph. And normally the instantaneous unit hydrograph has units of per time, and the instantaneous unit hydrograph has a number of properties. 1, 0 is equal or less than the unit hydrograph of time t minus tau, because L is t minus tau. And remember that t times minus tau minus t minus tau is 0, is almost 0. And this instantaneous unit hydrograph have some positive peak value if L is greater than 0, and it has some positive peak value for L is equal or less than 0, and as the L, that t minus tau, tends to 0, then U of L also tends to 0. And that one is very true, because you are not going to really have any response if really there has not been rainfall that has fallen down. And if you integrate the density function, you get a value of 1. And if you integrate the density function times time, you get 1, because integral ULDL is equals to 1. And then if you multiply by L, which is the time when the rainfall has fallen, then you get a value TL. You get a value TL. That is the duration, or rather the time lag of the unit hydrograph. And remember, U of L are peak values. U of L's are peak values. So this U of L here and L, or rather the L provides the basin lag or the lag time. And if you multiply the U of L times lag time, you get then the time of lag of the IUH. We have a number of methods of determining the instantaneous unit hydrograph from given excess rainfall hydrographs and direct runoff hydrograph. One, for an estimation of the IUH coordinate at time t is simply set to equal to the slope at time t of an S hydrograph calculated for an excess rainfall intensity of unit depth per time. And then B, the unit hydrograph, instantaneous unit hydrograph can be determined by various methods of mathematical inversion. For example, orthogonal functions like Fourier series and Laguerre functions. You can use integral transforms e.g. the Laplace, Fourier, and the Z transform. And then you can also use mathematical modeling related to watershed geomorphology. Yes, so I wanted to just mention the instantaneous unit hydrograph because it is a concept that if you advance your hydrology, you are going to come across a lot, or it is a crucial component of hydrology. Now, next week I want us to let me first check how much we have to do. We still have, after this, I think we are going to go to flow routing. We are going to go to flow routing. And here I'm seeing St. Venant equations. Did I teach them here or? Yes, we will do flow routing, both hydrologic, lumped and distributed flow routing. I want to check. Have I been able to give any tutorials yet? Because I want to give tutorials and I want us to now have a physical class so we can do practice with the convolution equations, and also we do some examples with I can now upload some of the revision questions, part 2. Hmm. 24. I'm going to upload some tutorials that we can start doing now, and then you can look at them before we have our physical classes next week, so that we can look at the tutorials together. And then during that session, I'm also going to explain how to expand the discrete convolution equation. Okay, I don't know whether I've sent. Yes, so those are some. I will be updating them later. And remember what we said about tutorial questions are a very important component of this course. Extremely, very important. Now, I want to take a roll call. And then I save attendance for today, and then we can discuss class attendance. We discuss class attendance. So I first of all edit, copy. I'm going to new, then I say those who are present so that you can know, edit, copy, you can know those who have. So we have who? Elisha Higgins, Gilbert Shivega, Hezron Kipruto, Mwiga Mutero. Hao wako tu wamejoin na wakaenda. Ni kama mtu amejoin tu na akawacha nini, anajoin anawacha kitu kirani tu kwa nini, kwa kabati, anaacha tu kipiga yowe peke yetu. Anyway, so now I want us to go to a session whereby we are, myself and yourselves, we are all clients of our timetabler. And, sometimes I sympathize with them because, in addition to us, they also have, for example, if you are doing common courses, other faculties have to also be included in our timetable. And especially when you're doing common courses, you find that civil engineering, survey, electrical, mechanical, nyi wote mnafanya course moja. So what it means, sisi, if you say mathematics is going to be done on Wednesday at 11 in civil, it has to be the same in the other faculties. So if for whatever reason, she allocates that time to, she gets a little bit, ambitious and assigns that course by herself without consulting the other faculties, then you find that there have to be rearrangements through and through. Yeah, so sometimes we just have to bear. Yeah, or understand. Because even if we didn't, what else can we do? Kuna kitu tunaweza fanya? I don't think so. So classes start from 7. They start from 7 to 5. I want us to help each other here. Seven, 8, 9, 10, 11, 12, 1, 2. So we take the rest of the hours to 4 to 5. We try and finalize this issue of timetable once and for all. And this class will be the first with me to do this.
Excuse me, madam.
Yes, yes.
What are you talking about? Because we don't know what you're saying.
Well, umeingia saa ngapi? Alafu umesoma WhatsApp. What I'm saying,
Yes.
last time we had agreed on timelines, vile tutakuwa tunapatana kwa class, but as you notice, every day I'm getting confused. Because when I think I had already blocked my calendar, and as according to the dates we had agreed, and times we had agreed. But once we have realignments in the timetable, then I'm left wondering on what to do. Like today, you have seen a lot of discussion on the WhatsApp that tuendelee tu na zile timelines tulikubaliana. But which timelines are they? Because now I'm totally confused because we have a new timetable. So what I want us to do is we look at the timetable together, and then we decide. We make a final decision together as a class that we are going to stick with. Is that okay?
I'm the classmate, and I told you earlier.
I usually discuss with the whole class. If you will allow me, because now I call the class and I want us to make a decision as a class, not with the class rep.
Madam, kindly listen to me what I have to say first. The problem is not the class, because we started our classes week 2, and engineering hydrology we started week 3. As we in week 2 already we had arranged all the classes with all the lecturers. So we are told we are doing engineering hydrology week 3. So we just fix engineering hydrology. We cannot mix up the other classes. And the lecturer already agreed they won't change the time.
Okay, Bomere.
Yes.
Hapa tunakosana kidogo, and that is why I don't like dealing with class reps. Because now you see we will be dealing, me and you, and I like dealing with classes. Because now we have a timetable.
Yes, we have a timetable. I've seen it. We are supposed to have a class on Wednesday. That's what the timetable says.
But
On
that
Wednesday,
is one. You see, I cannot finish engineering hydrology 1B with one class in a whole week. I need 2 classes. What
that's
is
what
so
I'm telling
difficult
you.
to understand? Because the only time we had agreed is an extra time on Wednesday.
Of course, when is the 1 hour?
Yeah,
Because
just
you are
1 hour. So where am I going to get the other hour? And the other hour is today. And I'm trying to say, so what do you want me to do? So because the other lecturers have taken time, I do not teach.
no, that's not my point.
Okay, so can I can also do this. I just let you people make a decision, whatever you want, if you want to learn, if you do not want to learn, because I want the class to have a discussion and I do not want to have it with the class rep alone. I usually deal with students directly, and I think I was very clear. And now for this person who is saying Thursday 2 to 4, because I need to also give you a schedule, I can give you a schedule, my schedule, and the times when my time I'm occupied, and then you can fix your time, ile nyi mnataka, that time when I do not have a class. And I'm kindly requesting you and I'm giving you a piece of advice. Usiaiambia mtu mwingine ati wale wengine wameshaamua. Mimi yangu naamua kulingana. I'm coming from the official communication to making local arrangement. So what I'll do is this. I will send you my schedule. The times when I'm free, and then that class of Monday, even that 1 hour, wacha tusiendelee nayo, I will just be okay with the 2 hours. I will give you my schedule and then you can allocate your class in any place where I have free time. Wacha ibaki hivyo. And class rep, me, I deal with students, I don't deal with class reps. Class reps wana deal na school. When it comes to me, I deal with each one of you. So let us do this. I will finalize the schedule and post my schedule on your WhatsApp. Na muniambie, and I want a participation of everyone in class. I do not want a communication from the class rep akuja niambie tunafanya hivi, because now that is not what I do. The other lecturers may do that, but me, I do things my own way. Okay, so we end the class now. Someone is asking whether it is a discussion. You see, I try to make the discussion, but your class rep tells me he is the one who is now, he tells me I'm the class rep. What do you want me to do? I'm trying to bring a discussion, nilete niwaonyeshe my schedule ndio hii tuweke wapi, but then I'm told no, we can't discuss because we came to fix your course later. Whilst me, I was waiting to follow the timetable. So I don't know how the discussion should go. Should I lead it? Should the class rep lead it?
Excuse me. Actually, excuse me, madam. I think you got me the wrong way. I'm just telling you the reality from what we had agreed earlier.
Bomere, if you can just let one of your colleagues even speak for one, because I will tell you, I like getting opinions.
No, my point is not that I'm trying to force you. I'm just telling you what they told me to communicate to you, but they can tell you themselves now.
Yes, that is, and the class, that is what I want us to do. Sasa mukituma class rep, how will I know that it is a whatever? For example, it is the decision of John Kimanzi. How will I know it is the decision of Kipkoech? Let me. And then Brian says here, I have made up my mind. If I had made up my mind, I would not have come. I would not even have proposed to have this discussion. And I would not even, because now I was just about to give you my schedule. Ndio muniambie tuende wapi. I wouldn't have. I do not, apart from today, 9 to 11, which is the official time, I do not know what other time, when other time. Now, Hunter, you say he speaks for the rest of you. What if I want to speak with each and every one of you and not one person? Is that possible? Is that possible? So I will send my schedule, mweke hiyo darasa ingine penye mnataka, and you will, or I will actually send the schedule and then you can put the 2 classes. At least give me 2 lessons. Give me 2 lessons in the week. That will be enough. Next week, based on whichever times mutaniweka, next week we are going to have a physical class so that we look at the tutorials already. We start looking at the tutorials. So let us end the class at this point. And hopefully I get a determination. I will get a determination by end of today so that I can plan for next week.